This morning. It's great to have you here. Over the next 45 minutes or so, Will and Leo from Elementa Consulting, who are the co-author of TM65, will provide an overview of TM65, as it says here, calculation methodology for embodied carbon in building services. This follows on quite nicely, actually, because a couple of weeks, 2 or 3 weeks ago, for those of you who joined, we had a fantastic webinar on Part Z, in which we learned about the proposed regulation of embodied carbon throughout the whole life cycle of an asset, as opposed to the area of building services that we're going to discuss today. Before I hand over to Will and Leo, just allow me to cover off some admin. As it says here, please leave your microphones on mute throughout the presentation. I've enabled the chat, so if you do want to ask any questions of Will and Leo, please put them in the chat function, and we'll probably raise those at the end of the session. As you heard, I am recording this session. Some people won't be able to make it, so we upload it to our YouTube channel and obviously onto MESHWORK as well. MESHWORK, for those of you who may well have just joined for this webinar, is a network that is pretty much for the community. It's a low energy and sustainable building design community. We want to encourage people to share learnings and come together with the aim of pushing towards, a carbon neutral world by building better buildings. We host regular webinars like this, try and put on at least 2 a month. I've got some good ones lined up for Q1 of next year. This is actually the last one of the year, the last one in December. I figure after today, people's attentions will be elsewhere. So thanks for joining today. If you do get value out of MESHWORK and the webinars and the chat and everything within the network, then please use your referral link within your profile settings, because we've grown pretty rapidly this year. We're now well over 1,500 members. Started off on around about 850 at the start of the year. So we've grown rapidly, and we thank everyone who's joined, because it does add to more and more chat. Let me just go on to the next stage. Mesh Energy set up MESHWORK. Mesh Energy itself is a sustainable energy consultant. So those guys are in the end of a phone or an email if you'd like to talk to them about any particular projects. But ultimately, it is independent of MESHWORK, and we are the platform that is open to everyone. And there's tends to be a lot of architects on the call, which is fantastic. Before we get started, please use chat functionality, say hello, introduce yourselves, say why you're here, and then, as I said, you use the same facility to ask any questions of Will and Leo as we go on. I probably will call time on that, and I will ask Will and Leo to share their screen so they can get started. Leo, you're on mute, but I presume you know that.
There we go. Can you see my screen?
Can indeed. Fantastic.
Perfect.
Cheers,
so hello everybody. It's Will Berry from Elementa Consulting. Also joining me will be Leo. We're quite heavily involved in this TM65 methodology. Elementa co-authored it, and we use it quite regularly. So yeah, if there's any further questions beyond this, we're always more than happy to answer them, be it as, again, answer emails, be in a phone call, whatever, talk about it. So yeah, generally what the session is going to be about is we're going to give a bit of a background to embodied carbon, why it's important, the challenges we specifically have within MEP, and then bit onto the methodology, and then kind of some case studies, how we've used it. Yeah, and then we'll have time for a Q&A at the end. So just for everyone, this is the document itself. It's a CIBSE published document. It's available for download from the CIBSE website. So again, if you are interested in this, I would definitely recommend going on there and downloading it and having a read through. There's a lot of detail in there. So yeah. So with that, I will hand over to Leo, and he'll take us through the first part of the session.
Lovely. Thank you very much. Thank you very much, Will. And yeah, so the first thing that I would like to start with is some definitions and just basically make sure that we're all on the same page when we talk about embodied carbon, when we talk about global warming potential and CO2 equivalent. So as mentioned, the title of this session is Embodied Carbon of Building Services, a calculation methodology. That's an introduction, but what do we mean by carbon emissions and embodied carbon? So first of all, let's start by carbon. When we say carbon, we mean greenhouse gas emissions, which are responsible for global warming. There are different types of greenhouse gas emissions, such as carbon dioxide, methane, nitrous oxide, and they all have a different effect on the climate, and climate change. But this is why we do convert these different gases in CO2 equivalent. And that is why we talk about carbon when we say, when we refer to emissions. So when we say carbon footprint, this is the sum of all the emissions minus the removals. So what you see here is just a breakdown of some of the most common gases that are being emitted, greenhouse gases. And what you can see there is the equivalent impact that they have in relation to our kind of basic unit of measure, which is carbon dioxide. An example is methane, which is usually released during decomposition of organic or biogenic material. You can see the impact associated is 36.75 times the emissions of carbon dioxide, and that's basically how we measure embodied carbon or any carbon emissions, in fact, and that's why it's called CO2 of kilograms of CO2 equivalent. So next slide, please. So then when we talk about carbon emissions, knowing that we talk about embodied carbon, CO2 equivalent, these are the emissions associated with the materials, construction processes through the whole life of an asset. In this case, we're talking about a building when we say asset, and the carbon emissions associated with the product making, construction, use, and end of life. Next slide, please. So basically, with embodied carbon and embodied carbon assessment, you assess the emissions through a life cycle, using a life cycle assessment. That's a methodology that we can deploy. And it's a method which is used to quantify the environmental impacts, as we mentioned, global warming potential or kilograms of CO2 equivalent through the life cycle of a building. In the case of a building asset or the built environment, the different stages of a life cycle are defined by the EN standard. We're talking about the EN 15978 when we talk about a building. And what the EN defines is the different stages or sub-modules that we need to take into consideration. So to summarize, for an embodied carbon assessment, you add the carbon emissions of the stages A, which is basically called upfront carbon emissions, and then B stages, which are called in use, and then C stages, end of life. Before we move to the next slide, I just want to point out that that dotted line that shows the embodied carbon emissions, you can see that it kind of snakes around those B6 and B7 emissions. Those are what we call operational emissions. That is not what we consider when we talk about embodied carbon or embodied carbon assessment. Embodied carbon assessment has to do with everything regarding to the material and material use. Okay, so operational carbon, we mentioned that is not part of the embodied carbon assessment. We saw that it was excluded from the previous scope boundary. Carbon emissions related to operational carbon is something that is relating to the energy used and water used during the lifetime of a building. And I'm sure that we're all familiar with what those are. And the focus around these emissions has been quite relevant, has been extended for a number of years. The focus of this session and the focus of today's efforts to reduce carbon emissions are shifting from operational to embodied, as is something that has not been historically accounted for. So if we go to the next slide, what we can see is the impact that embodied carbon emissions have paired with operational carbon emissions over the life of the building. So what is really nice here, and I think is quite useful, is the visual representation of, first of all, how the embodied carbon emissions and operational carbon emissions are distributed throughout the life of the building, but also the scale of these emissions. So what we can see here is that the upfront carbon, so A stages represented in red, is actually the biggest chunk of the emissions associated with the building when we talk about embodied carbon. That has to do because all of the materials that is required to build up a building are going to be poured into that stage pre-occupation of the building. But let's not forget that even during the life of the building, there are still some emissions associated with both the operational, and that's the orange that you see right there over on the chart, but also that light kind of salmon color graph bars that you see. And those emissions are related to the replacement, refurbishment, and just generally speaking, the upkeeping of a building. So if we think about a facade, that's a perfect example of where these emissions might be. We're talking about replacement of windows. We're talking about replacement of external doors. We're talking about the replacement of cladding and and shadings, if there's any. So that's where the emissions will be associated. Another good example is internal finishes. At the end of the life, we can see the emissions associated with the C stages, aka as mentioned, end of life. That's also quite a sizable emission, and that has to do with the decommissioning of the building. That includes demolition, but also all the different scenarios that each element and each material that was used in the building will follow to be processed and to be either reused, sent to a landfill, or incinerated, depending on what material will be. All of this obviously has an impact, and that's why it needs to be taken into consideration. The other one that I wanted to mention is the D stages, which is beyond the life cycle or beyond the project that we are assessing. When we look at any benchmarks, whether it's provided from the GLA, whether it's provided for RIBA or LETI, that refers to embodied carbon. We're always talking from A to C, so D is excluded, but nonetheless, it's a good indication of how good your building is in terms of circular economy and reusability of resources. So you can see here it has a slightly positive value, but most of the values are negative, and that's because we're assuming that materials will be reused and fed back into the economy. Some materials will be decommissioned through incineration when we talk about wood, and some of that energy will be retained and fed back to the grid. So all of these elements feed into this module and will be offsetting, aka having a negative value overall. Unfortunately, this is currently not accounted in the benchmark values that we see being circulated. Next slide, please. Okay, so why is the discussion around embodied carbon and more specifically embodied carbon in building services equipment is relevant? So next slide, please. So when we talk about carbon emissions, I think it's needless to say we're all aware that we are in a carbon in a global crisis. There's a need to reduce carbon emissions as soon as possible. This is just a visual representation using colors to represent the annual global temperatures. And as you can see, those are increases from 1850 to 2017. These values are informed by the IPCC report, which is basically a report that gives an understanding of how we are in relation to the that trend that is defined in relation to the increase in temperature globally. And we need to stay within a 1.5 degree increase, otherwise there's going to be serious consequences and irreversible consequences. And the output from the IPCC report is that the construction industry needs to reduce emissions by almost 80% by 2030 and actually become net zero by 2050. That is to avoid that 2-degree increase globally. Next slide, please. Okay, so we know that we need to reduce embodied carbon. How does embodied carbon fit into the conversation? So embodied carbon can be up to 50 to 70% of the emissions of a building over its life cycle. And it's actually of growing importance because we are all aware, or you might be aware, that there is a decarbonization happening from of the grid. And as a result of this, the associated impacts relating to the operational energy are actually reducing. And in percentage, the embodied carbon emissions of a building are increasing. What you see here is, again, another very good representation, which visually shows how much more relevant embodied carbon is becoming, and therefore the need to focus our attention on this side of the conversation, in this kind of side of the emissions. Okay, next slide, please. So embodied carbon of MEP. Obviously, lots of conversation within the embodied carbon space has happened for the structure, facade, and other elements in a building, which is great, but not so much around MEP. And actually, if you think about this intuitively, it's not straightforward, and it can actually be quite high. So in this slide is actually quite interesting because it gives a good representation of the actual impact associated and the weight associated with MEP. So if you think about the quantities of MEP and how much stuff there is in a building, it's really hard to grasp. This is one of the building elements that is not exactly visible. It's most of the times is hidden, and most of the times it's quite hard to get an understanding of what exactly goes into a building unless you're in the sector or unless you're an MEP engineer. So just to give you some perspectives, a 2,000 meter square building can have up to 25 tons of MEP equipment. As shown here, it's almost the weight of a fin whale. Before we move on, I just wanted to clarify that the issue with the MEP and embodied carbon in MEP is that there are some figures that give an understanding of roughly what's the impact associated with MEP, and that is between 15 to 25 kilograms of CO2 per meter square. But the issue is that that does not allow us to make comparisons of different systems, and therefore guide us through the design processes and guide everyone towards reducing impact of the MEP as well as other elements of the building. Okay, so that's basically the first thing that we need to consider: big quantities. Second one is high impact materials. So let's think about MEP and let's think about the materials that goes into MEP. That's pretty straightforward. It's usually metal, it's usually plastics, it's usually aluminiums, it's usually materials that requires high energy for their production. If we think about metals, the biggest source of emissions in the production of metals is this melting process, or the melting process that happens to form a metal element, such as casing in the context of MEP. When we talk about aluminium, we're talking about both a high melting temperature, but also high emissions associated with sourcing this material. Copper can be the same. Electrical equipment uses rare earth material and materials that are quite hard to source. So you can start to kind of build a picture of why MEP needs to be considered. If we pair those big weights, big material quantities with a high impact of these different elements, already we can start seeing how important this conversation must be. And then the next slide also shows the third element that actually breaks down or gives us an understanding of how important it is to consider this, aka the high replacement rates. Let's not forget this is a life cycle assessment, therefore we're considering the whole life of the building, and that includes replacement of damaged items and of items that reach the end of life over 60 years, which is the period of assessment for an embodied carbon assessment and life cycle assessment alike. So in this slide, we can see different elements of a building: a skin, structure, fitting, interiors and services, and site, and the different life of each one of these elements. MEP is something that has high replacement rates. So this is basically the last piece of the puzzle that justifies the need to concentrate our attention: high material weights, high impact per material, and a big number of replacement rates. All of this basically paints a pretty clear picture, aka we need to concentrate our efforts to understand MEP impacts and give more granularity to what we understand within the MEP systems, so that we can move towards a lower carbon solution. Next slide, please. Okay, so this basically just also brings into the conversation of why there is a need for whole life carbon approach, especially when we talk about MEP. When we talk about MEP, the choice of your system has a direct impact not only on the materials that will be required to produce this system, but also on the associated operational energy that will be required for the life of the building. Therefore, the need to have a whole life carbon approach where we pair the impact associated with the embodied carbon as well as the impact for the operational carbon. There's always a best solution, and it's a fine line to walk between selecting the best option from a material perspective, aka embodied carbon, but also from a operational and energy perspective. So therefore, why the need to put everything together and considered whole life carbon emissions. Okay, before we're going into the detailed calculations or more detailed calculation and assessment, there are some straightforward design approaches that you can take to reduce MEP even before going into any sort of calculation. So the first one is less is more. So we already know that MEP has a high impact. We know because of the high material quantities, but also the high impact of each material. So it's a pretty straightforward concept. If I reduce the need for MEP, I automatically reduce the need for materials, and therefore I reduce the impact of my MEP system. So try and keep in mind the fabric first approach is usually good when we talk about MEP. Next slide, please. Think circularly, or think about circular economy. Specify products and components that can be demounted, can be reused and disassembled, and the materials that can be recycled. Ensure easy access for inspection and maintenance and replacement. An example of this is mechanical fixing instead of chemical bonds or chemical fixing. So if you are ever faced with a choice of, do I use a nut and bolt or do I use an adhesive? Know that adhesive usually tends to be a non-reversible method, and therefore disassembly will not be possible. Obviously, this is a very straightforward example, but it's a generic kind of approach that you can take when thinking about MEP. We also know that one of the reasons why MEP is very impactful is that it has high replacement rates. So if we think circularly and we think about repairing rather than replacing, that's already a big impact to reduce the overall material use throughout the life of a building. And then the next slide, please. Mitigate refrigerant leakage. So you might be familiar or might not about the conversation around refrigerant leakage, especially since we're moving towards decarbonization of the grid, and especially since we're using more and more ground source heat pumps, air source heat pumps, and generally speaking, MEP equipment that uses refrigerant. That is great because it has a great positive impact on operational, but let's not forget that refrigerant leakage has an incredibly high negative impact on the environment that falls within the embodied carbon kind of set of calculations. So always try to specify a low global warming potential refrigerant. The best option that you can go for is probably CO2 because it has an impact of 1:1. Just to give you some examples, there's some refrigerant out there, which such as R32, that have an impact of 2,000 or more global warming potential per kilogram of refrigerant, and that already paints already gives you an understanding of why this is such an important element, especially if we consider bigger systems where you can have 60, 70, even 100 kilograms of CO2, and the leakage does become quite relevant. And then finally, the conversation about low embodied carbon materials. So again, referring back to those three kind of pillars of why MEP is important, one of those was the impact of the material itself. If we can have an impact on the material that we use for our MEPs, we automatically can have an impact on the a positive impact on the system embodied carbon emissions. So usually most materials use most MEP elements use stainless steel, aluminium, brass, zinc, which are very recyclable and are usually a good option for more extended life periods. But if you have a life, or if you have a refurbishment life, or if you have a Cat A or Cat B commissioning that that has a lower life cycle, try and make a conscious decision on, am I getting the best use out of this material? Is my high production emissions at the beginning of life justified for the life or for the number of years that this element is being used? Or is it possible to deploy another type of material, which yes, might have a shorter lifespan, but might be better selected for your application? So low embodied carbon material is just basically wants you to prompt you to think about what material selection does, and the fact that it's not always a straightforward answer. You need to think about what you put into a design because it has a direct impact on your system emissions. Okay, so we talked about the reason for why we need to concentrate about embodied carbon. Before that, we gave some definitions so we're all on the same page. We talked about why embodied carbon of MEP is so relevant. How do we account for MEP and how do we account for the associated emissions? Now, you might have heard the term EPD, which stands for Environmental Product Declaration. An EPD is a standard way to disclose environmental impacts about a product through its life cycle using a consistent methodology. And consistent methodology is really the part that I want to kind of stress on. Consistent methodology is what allows us to make like-for-like comparisons. If we don't have a consistent methodology, unfortunately, making reasonable and guided information as to what we want to specify becomes almost impossible. Now, an EPD is governed again by an EN standard. So we talked about EN 15978 when we talk about buildings and building systems. For products, we talk about a different EN standard, which is closely related, but it's EN 15804. The thing that I want to point out is that even when having a standard that regulates the development of an EPD, direct comparison and consistency of the methodology is still an issue. Next slide, please. So what an EPD provides is information for different environmental impact indicators. So global wind potential is one of those, but also acidification potential, eutrophication potentials, and others, as you can see there. So it's a pretty substantial table that you can find there. And it's also broken by life cycle stages as defined by EN standard. Now, these are all great, and these are all great resources. If you want to look at what different EPDs are available, there's a number of free to access resources that you can gain access to. One of them is the Eco Platform, which is a Europe-funded initiative to gather EN compliant EPDs. There's also IBU, which is the Institute Bauden und, I'm not even going to try and pronounce that. And then we also have the INIES, which is a initiative which started in France. They use a slightly different definition for EPDs. They converted it in French, and in French it has become PEP. But nonetheless, that is also compliant with the EN standard. Therefore, it does fall under the category of EPD. And then again, green premium product. That is just some of the resources that you can find. Okay, so before I hand out to Will, I just want to say EPDs are great. EPDs are the way forward. EPDs provide a ton of information about embodied carbon. The issue is they're extremely costly, they're extremely complicated, and is not something that we can do right now for all MEP products. Therefore, CIBSE TM65. And I'm now going to hand over to Will.
Thank you very much, Leo. So as Leo said, EPDs are the first port of call. So if a product has an EPD, we should use it because they're the most robust data source we have. However, like as Leo mentioned, EPDs are really difficult to make. They're time consuming. And so MEP specifically has kind of fallen behind in this. And a lot of the time, EPDs just simply aren't available. So the idea of TM65 is to provide a methodology that allows for an easy calculation that can be used in the analysis of systems and to give designers a kind of a base point to understand what the impacts different systems will have. So TM65 is, we're only interested in looking at global warming potential. It doesn't consider any of the other environmental impacts that an EPD would. And so in that case, like that's one of the things, it's one of the simplifications, just makes it easier for us to use this. As Leo's also mentioned, like it's really important that we do this because of the massive weight of MEP. It's also really important that any methodology we use is consistent. So we can't be used, so if we're using TM65 methodology for MEP and then a different methodology for other aspects of the building, like the results become meaningless. And so we have to ensure that the results you get from TM65 are somewhat comparable to EPDs, etc. So for TM65, we are only interested in the embodied carbon. So we're only interested in the A stages, B stages, and the C stages. That doesn't mean that the other parts aren't important. And as we'll come on to later, there's really interesting interactions between where there's a payoff between embodied carbon and operational carbon, and that's part of what the designer needs to consider when making choices. So there's the basic methodology for creating TM65, and it all starts with data collection. So talking to manufacturers, and having a manufacturer engagement. Basically, a manufacturer needs to provide a certain level of information in the form of a TM65 manufacturer form for the calculations to be able to be done. And then depending on the level of detail that the manufacturer has provided, then that can be, we can either perform a basic calculation or a mid-level calculation. And each of these have different levels of certainty. And as you'll see, they have a slightly different impact. But then this is reported and used in projects, and also reported to CIBSE, and so it can be used by the wider industry. So here's a really nice visual representation of the difference between basic, mid-level, and EPDs. So a basic calculation is really easy for a manufacturer to do. So all you need is basic information about the product. So things like the type of product it is, the material breakdown within the product, so how much of it is steel, how much of it is plastic, just as a percentage, the product's weight, and that's pretty much it. The issue is that obviously with that, there are a number of big assumptions that have to be made, and therefore a basic calculation tends to give a higher embodied carbon result than if you went for a mid-level calculation. A mid-level calculation is like a kind of a halfway house between the basic and EPD. It requires a little bit more information from the manufacturer, so providing things about factory energy usage, assembly location, all that kind of stuff. But it provides a slightly more accurate result. Obviously, neither of these are as accurate as an EPD, but again, that's much more difficult for a manufacturer to produce. So they're much less common. So here's basically a table, as can be found in TM65. It gives you an overview of what the differences are between them, what's included, what's not included. You can see on the left side that's the basic calculation. So we're really only considering the basic makeup of the product. The mid-level calculation in the middle, a bit more detail, and then on the right is the EPD, and that's got a lot of detail, but again, very difficult to come by. So the process is, for when you're thinking about you might need some embodied carbon information from a manufacturer, you first of all will check that if they've got an EPD. If they have an EPD, you should use it 100% because they've gone to the effort of making it, and it's a really accurate and great source of information. If they don't have an EPD, this is where we need to have a bit of manufacturer engagement. So you will send across the manufacturer form. You can have a conversation of how to fill it out. They will basically need to provide, as a bare minimum, is section A, which is the material breakdown for the product. If they've more engaged or have the information more readily available, then they can also provide enough information for sections A and B, which also includes details about the factory and factory location, etc. Then you can perform the calculations using the methodology. And then the final step is to report this information to CIBSE, and this can be kind of collated into a CIBSE database, which even though that specific information won't be distributed, a generic data point will at some point be created and then shared with the industry as a whole. So we can kind of get better benchmarking. So as I mentioned, these are the three sections for the manufacturer form. So A is the compulsory thing. So when we talk about the material breakdown, we're talking about getting 95% of the material breakdown. The other 5 is if you can't get 100% and you only have 95% of the material. So you say, that it's 80% steel and 15% plastic, then the other 5% is assumed to be steel because that's the most common material with a reasonable global warming potential in MEP. If you can provide a bit more information, that's section B, and it's like the energy use in the factory, and then we basically get a better estimation of what the embodied carbon would be. And then C is currently at a very optional stage, but it could potentially be used in the future. And it's basically tracking things like waste output from the factory, water consumption, renewable production of energy on site in the factory, all that kind of stuff. So currently section C doesn't go into the calculation, but again, it might be in the future, and it's a really good thing that we want to be tracking this information ahead of time before we actually need it. So this is a kind of a visual representation of how a calculation works for the basic methodology. So on the left-hand side, we've got the step 1 and 2, which includes the material extraction and repair rates for the product. We then apply a scale-up factor to this and a buffer factor to kind of account for the fact that all the complexity in the system and all the other variety of things, and the fact that it's a basic calculation, we need to be very conservative with it, because obviously we've got low level confidence. And then finally, we would add on the refrigerant leakage. And again, there's a whole methodology specified in TM65, which gives us, for different types of product, it gives us like refrigerant leakage rates. So it's kind of standard across all different calculations. So here's, again, this is available in the document. It gives us a breakdown of the material embodied carbon coefficients, and these have come from the ICE database, and they're global averages. And so they kind of, it's reducing the complexity of the calculation again. So while one manufacturer might say that their steel has a lower value than this, it's all about consistency between them. And if they really wanted to show that, then an EPD would be the best way of showing it. The complexity factor, this is dependent on the product type. So with this, we're trying to capture the length of the supply chain to the final assembly factory. So for a very simple product, like a pipe, obviously the supply chain is going to be a lot smaller than if you've got an air handling unit or a heat pump. And therefore, the scale-up factor will vary. For the mid-level calculation, we've got a bit more confidence in what's going on. And so we only apply the buffer factor. We don't need to really account for this, for the scale-up factor, because we've been provided this information. Refrigerant leakage, as I mentioned, these are the standard, this is a standard thing across all calculations, and depending on the product type and whether you're charging your system on site or if it's a pre-packaged, pre-charged system. Basically, we also require the manufacturer, if they have refrigerant in their product, to specify the type of refrigerant. We will then use the refrigerant leakage combined with the weight of refrigerant in the system, and that the factor, the embodied carbon factor for the global warming potential factor for the refrigerant, to work out what that refrigerant leakage will be. Again, all these assumptions are found in the appendices of TM65, so I definitely recommend having a look at that. Then, as I mentioned, once you've done all these calculations, it's really good for us to send this off to CIBSE. And so when you're filling out a manufacturer form, there's a little consent box at the bottom, which you need to tick to say that you're happy with this to be shared with CIBSE and be used in CIBSE database, and there's a whole thing about confidentiality in there. So this is an example of a basic calculation versus a mid-level calculation. So as I mentioned before, the basic calculation will tend to overestimate what the embodied carbon is for a product due to the uncertainty. The mid-level calculation provides more detail and it's more accurate to what the actual embodied carbon for the product probably is. So this kind of just encourages people to, if they possibly can, to provide a mid-level calculation. So so this is for kind of, if you're a more advanced user, if you're not just, creating a single data point, and this is something that we've been working on quite a lot recently, is trying to create like a generic data point, which is really useful for early stage design. So when you're going to have a heat pump of a certain capacity, but you don't necessarily know which manufacturer it's going to be, it's really useful just to have this kind of, oh yeah, a 20 kilowatt heat pump is about this. And so by using the previously stated methodology and by using averaging, or like however there's different approaches to do it, you can come up with this kind of generic value. And this is something that, again, we're working currently on CIBSE to provide a database for. So we talked about the methodology a bit. Last year, we, alongside CIBSE, produced TM65.1, which is kind of like a demonstration of the methodology and it being used in practice. It's a study looking at the embodied carbon of building services, residential heating. The study, again, is all available on CIBSE to download, and you can have a look and proper read through. Basically, we compared a number of different heating systems for residential use, both individual systems and communal systems. Here's an overview of the systems. We went through the whole process of contacting manufacturers, asking them if they got EPDs, and if they didn't, talking through making TM65 forms, and then we went on to produce generic data points. We then used these generic data points to combine to create system-wide values. So for example, for 100 unit apartments, for a gas boiler, what's the embodied carbon per square meter? Next slide, sorry. So we also produce these graphs, which are a nice visual representation of how generally products, the embodied carbon of different products maps across their capacity and also across their weight. So the graph in the bottom right shows quite a nice linear relationship, straight line relationship between the weight of a product and the embodied carbon. Now, it can be quite useful. So if you're just trying to do a really high level calculation, you can just understand the weight of your MEP system and find in the next slide, there's an average embodied carbon per weight of 9 kilograms of CO2 per kilogram of MEP equipment. And you can just simply times that by that. But obviously that gives you a really high level calculation. The other thing is we've also looked at how kilowatts or the capacity of different products relates to its embodied carbon, and that's not such a linear or straightforward relationship, and that's something that we're actually working on a bit more to understand. Again, all of this information is available to find, and you can see in TM65.1 we came up with these are the generic data points. So it gives you, if you're looking at an air source heat pump, roughly what the embodied carbon is per kilogram of that heat pump, and also kind of gives you our confidence in those values. So you can see that for some we're much less confident and others we're much more confident. So here are the results from the study. And again, I'm not going to go into detail about these right now, but I think the really important thing to note is that this is just part of the picture. So while some systems here look really attractive from an embodied carbon point of view, we need to also make sure we are considering the operational carbon in this and bringing the two together and then choosing our designs based on that. It's also a really interesting relationship between, especially in the communal systems, between the scale of the project and the number of units that the communal system's feeding and the embodied carbon. So obviously you get a more bang for your buck with bigger systems for bigger schemes for communal systems. So if you've got a 2,000 unit scheme, then you get much less embodied carbon per square meter than if you've got a 100 unit scheme. It might seem obvious, but it's a good thing that we didn't know until we read this study. It might have thought it, but we've now kind of confirmed it. So just quickly, and finally, we'll just run through like how we've created these generic data points for different products, and kind of the importance of doing this in a fair way. As Leo mentioned, and we've mentioned before, you've got to make sure you're comparing apples with apples, and you can't be comparing different products. That's the real key thing. Is if you are interested in doing these comparisons between products and making generic data points, you need to make sure and talk to the manufacturers to make sure that what you're comparing is fair. For TM65.1, we grouped all the products dependent on the capacity and the type, and then took like a weighted average and bought lighter products. We weighted lighter products up and heavier products down to try and mitigate that difference. We are currently producing the next document in the series, which is going to be called TM65.2. We will be looking there at the embodied carbon for an office scheme. So again, it's a very similar thing to TM65.1, except for we'll be looking at all the mechanical systems in there. We've taken a slightly different approach for creating genetic data points in that one to do with regression, but when that comes out, I'm sure like everyone can have a read of it. So I think that's pretty much our presentation. We open the floor to some questions for the final 10 minutes, and yeah, thank you very much for listening.
No, fantastic. Cheers, guys. Hell of a lot of information there. Thank you very much. Are you okay just to stop sharing your screen, Will? Thanks. Robbie's asked, I don't know whether you can see that, but I'll read it out. It says, do CIBSE TM65 reports currently work in whole life carbon assessment software such as OneClick, LCA, or I've just lost it, or will this be a future aspiration?
I think integration with OneClick, I think there have been conversations to include that in OneClick. I don't think that the level of, as you can see, there are two different ways that you can record information. There's a basic and there's a mid-level. And unfortunately, unless you go into the mid-level, the breakdown and the granularity that you have for the different life cycle stages is not exactly in line with OneClick. So unfortunately, it's a process that needs to be paired with the embodied carbon calculations that you develop in OneClick. So what you can do is you can extract the values from OneClick from which you have omitted the MEP assessment, and then pair it with your MEP values that are stemming from the TM65 methodology. So that's basically currently what we do internally, and we do recommend doing if you want to do an assessment. The other thing is that I believe that there is going to be, a development of EPDs and more kind of work done in the EPD space, and that's where kind of OneClick will be looking into to integrate. At the moment, though, I know that OneClick doesn't have a ton of information on EPDs, on MEP and MEP equipment when it comes to embodied carbon assessment. So, yeah, I totally understand that it would be useful, but unfortunately, it doesn't kind of qualify with their requirements, because I think they're quite stringent and they do always want something that is closer to an EPD. And that's, as we clarified previously, this is not an EPD and it doesn't try to be an EPD.
And then from an EPD perspective, this might be a really naive question, but the manufacturers and suppliers who undertake EPDs, they're presumably pretty confident in their products in terms of, they're trying to ensure they're have as low amount of embodied carbon as possible. Is that so they then become a preferred supplier, or is that have I got that completely wrong?
Well, from conversation with manufacturers and from conversations with, in the industry in general, I think that it's not even just about someone that has a better product will do an EPD. I think the advantage is already in having an EPD to start with, especially if you're an MEP manufacturer. So you might not be the best, but if you can't demonstrate how good you are, it doesn't really matter you claiming to be better than the next person. So I think the best thing to do to start with is, if you have the resources, do an EPD, and already you will be able to show that and provide that at a procurement stage, and already you're going to be a preferred kind of supplier than the next person, because the next person, you will have to do the work if the manufacturer does not do an EPD. So that already in itself is something that puts you in a better position. Okay, thank you, Cheers. Simon asked about the exclusion of B4 and B5 from T65, and why is that the case? So when we talk about TM65 and not 65.1 or 2, we talk about product embodied carbon assessment. So B4 and B5 mainly relate to the use of this product within a system. So B4 has to do with the repair, and B5, refurbishment, and the other one is repair. So they have to do with how many times within a certain system you will replace the said product. And that's why it is excluded, because it's something that is very specific to your building rather than something product specific. We do have some entries within the product the TM65 values themselves, and that has to do with repair, but that is not to be confused with the refurbishment and repair within a building. That has to do with the upkeeping of that product in itself, aka if we know that an air source heat pump can last 20 years, but you need to replace the compressor every 5, that's where you would feed that replacement. But it is not to be confused with a system level replacement and refurbishment. That's what B4 and B5 is. Also, A4 is not included, and that's transport from the manufacturing site to the site. That's another example of how that is very dependent on what type of building you're assessing, and that's why it cannot be included at a product level.
Is that okay, Simon? Cool, thank you. This might be the last question, just because you guys have filled the hour completely. Ronan have you read Ronan's point there, as opposed to me reading the whole lot out? But for the other people on the call, he's saying, I found that a lot of manufacturers are unable to provide accurate information about the material breakdown of their products. In this case, it's recommended to look for similar products on the market and make some assumptions, as we said. Often clients specify to use what materials and plant they want to use, but still need embodied carbon figures. What approach would you recommend?
I think that's a really tricky one. Obviously, I think it is something that we've come across as well when talking to manufacturers, that some are simply unable to give us accurate enough information. And in which case, like, there's really very limited stuff you can do for that, apart from, as you said, looking at comparisons with similar products. And I guess that's where these generic data points come in. So you kind of, you know roughly what a product of a given capacity is, and therefore you can kind of use that and maybe add a buffer factor onto it. So because of the lack of confidence. I would say, however, that as like more requirements come in, that embodied carbon information is required, manufacturers are going to have to do this, and so there is going to be a need. There's going to be, I think, it's going to become less of a problem that the information won't be available, because they're going to have to do it. Otherwise, they'll be just left behind in the market. So.
Cool. Okay. Thank you. Just lastly, I don't think there are any more questions from the floor. One of my colleagues asked, is the intention of the TM to be used to calculate the core building services contributions to MAT 01 in BREEAM, or is that not relevant?
Conversation has happened with BREEAM. Currently, TM65, you can find, if you control F on the GLA whole life carbon assessment, you will find TM65 as a recognized source of embodied carbon emissions for MEP. So that's already a step in the right direction. When it comes to BREEAM, I think it's a little bit tricky, just because there's the whole aspect of comparability and of different systems assessment. So I think they're kind of holding off to see what's going to happen next, how viable it is, what's the uptake in the market. I think this conversation and this justification is kind of outdated, because now we can see that a lot of manufacturers want it. Consistency is something that we do have within TM65. I cannot see this being something that it's not going to be at least acknowledged by the BRE for a long time, especially considering that I think Impact Database is very consistent, is very solid, but it has no information on MEP, very limited information on other building elements. So they are looking to expand this. Already, one click is an accepted way to compare different elements, even if they, not necessarily is arguably from my point of view, is not the best one to do a comparison. So the short answer is we don't know when and if that will be taken on board. There's also another conversation around, you know, for BRE for submission, you need to have one-click or eTool, because you basically link your Excel spreadsheets to their own MAT01 submission Excel spreadsheet. So it's an interlinked conversation. So it's kind of the intermediary step would be include that in one click, and once that happens, BRE would be more inclined to take that on board. But at this point, we can't really say whether or not. What we can say is that there's already an addendum that has been published for the use of TM65 in other locations. So the focus of the addendum is in Australia, but we also provided guidance on how to use this addendum in other part of the world. And I'll let Will speak, because he's been more heavily involved in this than I have.
Yeah, so it's basically, as they said, like it's a document which lets us adapt, or anyone adapt TM65 to different regions as well, changing some of the assumptions. And as Leo mentioned, it's already been used in Australia. So there's the TM65 version in Australia, and currently CIBSE's in conversations with ASHRAE in the US and Canada, and so it's going to be probably taken up there as well. So it's really good to see that the methodology is like becoming kind of like a standard, not just in the UK but globally. So yeah, these conversations are ongoing, and I think we're still in the early stages of it, so it's exciting times.
No, indeed. No, thank you for answering that one. Cheers, guys. I'm going to upload your deck and the documents as well from the TM65 website. If you'd like to add your contact details, or I can include your contact details if you wish, just so if anyone wants to get in contact, you're happy for that to happen, then then I'll make that available for everyone. But really appreciate the time and effort that you've put into today. It's much appreciated. It's gone down well, and I'm hopefully the last in this mini series, I'm trying to get hold of someone regarding the UK net zero carbon standard as well. So it'd be quite nice to finish off this little series with a talk on that as well. But no, thank you all for attending. Thank you, Leo. Thank you, Will. Really appreciate it. I think it's been very informative, as Simon has said himself. So yeah, everyone, this is the last MESHWORK webinar.